In this video on static electricity, we're going to do some stuff with electrical field strength, and especially that field strength due to point charges, and we're going to draw some electric field lines, those crazy field lines that don't really exist, but they help you understand what's going on with electrical fields. If you're following along in your ISM note packet, that's on pages 152 to 156. So for electrical field strength, let's just define or talk about what an electrical field is. And so if you got a charge sitting there, there's a magical, almost electrical field that exists around it. And if you bring another point charge into there, then it's going to feel a force because of that other charge that's sitting there. And to show you a picture what that looks like, I'm going to draw one for you. Let's call that figure 6.9. Let's say that you've got a positive charge here. If you have a little point charge, by point charge meaning it's small, it's going to feel a force going that way. So that's also the direction of the electric field. If you have another point charge here that's closer, it feels a stronger force, which would be directed away from it. If you had another positive point charge that was even closer, it's going to feel an even stronger charge that's directed away. So the electric field is always directed away from a positive charge. If you have a negative charge, and let's say you've got a little guy over here, then if this is a positive test charge, it's directed towards it. Another charge that's closer, stronger force. And another charge, an even stronger force. So negative charges have an electrical field that goes towards it. Positive charges, electrical field, we say, goes away from it. The next thing that I want you guys to know, if we're going to define the electrical field strength, it is this. I think you've got this written down already, but it's the force per unit charge. And the equation for that is that electrical field strength. Let's go to another page actually. Electrical field strength is the force per unit charge felt by a test charge, and that's going to be in the units of newtons per coulomb. This is very similar to gravitational field strength, which you might know as G, which is measured in not newtons per coulomb, but newtons per kilogram, or meters per second. If we're going to calculate the electrical field strength to a point charge, then we're going to start with a problem by our good friend Mr. Dickinson, which is this here. You may want to pause it, see if you can solve it. Do that now. Hopefully you've done it. Let me show you. Hopefully you've got the same thing that I'm going to show you right now. If you have your equation, which is this, you have to fill in the equation that you know for force from Coulomb's law, which is K, charge of your source, got your little point charge, and the distance away they are, but we're still divided by this point charge here. Now this is the point charge, so these, they cancel, they go away. So we're left with this equation for electrical field strength. Now the IB doesn't give you this in the data booklet specifically, but this here, which they do give you, turns into this if you're dealing with point charge. It's a useful one to memorize. Then you just fill in the numbers. K, this is 8.99. Charge is microcoulombs, so we got to go times 10 to the negative 6th. And it's all over a distance of 0.4 meters squared, and then you end up with a giant number, like 1.1 times 10 to the 6th. With electrical field strengths, you will often have large numbers. And it's easiest to represent these electrical fields not with numbers, but just by drawing electrical field patterns. So we're going to call this figure 6.10, and if we just have a point charge here, then the electrical field lines just emanate, it's a good word, away from it, symmetrically. And you can draw as many as you want, as long as they're symmetric, and you just want to know this field is weak, out here, where there's not many field lines, and it's strong close in, where you have a high concentration of the field lines. If you have a negative point charge, then it's the same thing, it's just they're all directed in. We draw the arrows going in. If you have something that is maybe twice as charged as this guy over here, same thing, you just have to draw more lines and show the higher the concentration, it's like a giant spider, the stronger it is. If we look at something more complex, let's say we've got two charges near each other. This might be called a dipole. Then the charges will come out of the positive and into the negative. They'll go up and they'll bend around. They'll bend around. And this might bend off the screen and come back in. This and come back in. Something else come back in. And if you had two positives next to each other, these field lines would almost cancel each other out. And so it might start off straight, then bend away. This is bending away. They're all bending away. And here in the middle, you have no field because it's canceling out. And let's do one more. If you have parallel plates, which is what we call a capacitor, then you're going to have electrical field lines coming over this way, and it's a uniform field within here. However, they do start to flare out a little bit on the ends. If you have, not a sphere, that's a sphere, and it's hollow, you've got, treat it like a point charge with field lines going in towards it. But what's important to know is that inside any metal cage, there is no field.